climate change becomes a growing issue, the people of the world have an obvious reason to use electric vehicles. They do not utilize gasoline or emit harmful gases. Prices of electric cars vary, with a Tesla at about $70,000 and a Mitsubishi IMIV at about $25,000. Generally, the higher the price, the longer the cruising range. Tesla has about 250 miles, while the Mitsubishi comes in at about 59 miles. Overall, another advantage of using electric vehicles is that the cost of running a car is much cheaper than gas, about $540 per year as opposed to $1,400 per year. Before we go into detail about lithium-ion batteries, let's first talk about the general design scheme of electric cars. Most differences lie within the propulsion system. Instead of having an internal combustion engine as a power source, electric cars often have one or multiple electric motors to drive the wheels. Fuel is no longer needed, and in place of the fuel tank, batteries are implemented. Since the engine is eliminated, a lot of accessories that are coupled with the engine, such as the cooling system, heat pump, alternator, and exhaust system, are not needed. This also means that the batteries are required to provide energy for air conditioning, heating, and all other utilities on the car. Replacing the engine with electronic components also means a reduction in moving parts and thus can potentially increase the reliability of the vehicle. Lithium is the 35th most abundant element on Earth and has a significant presence in seawater, totaling up to 230 billion tons. Currently, most lithium is produced through extracting and concentrating brine from underground pools rich with minerals including spodumene and petalite. Then, metallic lithium can be obtained through electrolysis. This production method is quite energy intensive. However, take into consideration the fact that each car only needs around 10 kilograms of lithium in all of its batteries, and the fact that batteries can last for a reasonably long period. Overall impact on the environment is relatively small. Now that we've looked at electric cars, let's take a look at what powers them. In their most simplistic state, lithium-ion batteries consist of a negative and positive electrode with an electrolyte between them to conduct the electricity. The electricity is the movement of free electrons. The electrodes are at different potentials, thanks to the composition of said electrodes, and the electrons will flow from the more positive electrode through the electrolyte to the negative electrode. If they're rechargeable, when hooked up to an energy source, the forced reverse flow will recreate the original potential between the two electrodes. To address what happens chemically in the electrodes, there have been studies done that tell us lithium ions can move very quickly when they are placed in a lattice structure that houses transition metal ions in mixed valence states. When the lithium ions are placed in this lattice, this causes the transition metal to be reduced, and when they are removed, the transition metal is oxidized. The lithium-ion part of the battery is found in the positive electrode. Why choose lithium? Lithium has the lightest weight, highest voltage, and greatest energy density of all metals. This makes it a great candidate for car batteries. But why are lithium-ion batteries specifically so great? What actually makes them better than the rest? We know that three main things can be done to improve the efficiency of a battery. Number one is having the greatest difference in potential possible between two electrodes. Number two is having the lightest weight and smallest size ions traveling back and forth as possible. Number three is the ability to have an electrolyte that does not run out, i.e. is not used as a reactant in the battery's chemical reactions. This was the sticking point for a lot of earlier, more popular battery technologies. In lithium-ion batteries, however, the lithium ion is moved back and forth from both electrodes, and the electrolyte is not used as a reactant in the chemical processes. As mentioned before, the best thing about lithium-ion batteries is their high voltage and energy density and low weight. However, lithium-ion batteries have several other advantages, including a low self-discharge rate. This means that it takes a long time for the electrodes to lose their charge by themselves, i.e. when not actively being used. Lithium-ion batteries also require little maintenance and are extremely versatile. A phenomenon that is prevalent among rechargeable batteries is called the memory effect, meaning that a rechargeable battery will never hit its peak capacity again if it is consistently partially charged. Lithium-ion batteries have a particularly high resistance to this effect. They also take less time to charge and have a longer lifespan when compared to other types of batteries.
There are many challenges for electric vehicles, which have resulted in their lack of popularity versus conventional cars with internal combustion engines. Electric vehicles lack the freedom that conventional cars provide, due to their lower range and how few public charging stations exist. In the US, there are only 110 public charging stations versus over 121,000 gas stations. The main challenges that electric vehicles must overcome to gain the popularity that conventional cars have are slow refueling, capacity and energy density, and consistency. The issue with capacity and energy density is that with current batteries, there needs to be a balance of mileage and weight. Too big of a battery is heavy and hinders travel by forcing the engine to carry more weight, but too small of a battery decreases range. Improving the optimum of this requires an improvement in the material science of lithium-ion batteries. So, how do we make lithium-ion batteries better? The answer lies in the material science paradigm of structure, processing, and properties. Looking first at properties, there's a substantial difference between using graphite or silicon for the anodes. Graphite is currently used in many lithium-ion batteries due to its high stability. However, it absorbs far fewer ions, which reduces its capacity. In contrast, silicon anodes can absorb significantly more, but this eventually destroys the crystal structure of the silicon, resulting in severe mechanical stress, making it much less stable than graphite. Considering processing, silicon anodes can be improved by using thin films of silicon, roughly 20 nanometers thick, because that is all that is needed for the maximum absorption of lithium. Any thicker has a layer of silicon with little to no lithium absorption. This cuts down on material and energy cost of the anodes, although it does not increase their stability. This connects with structure. Several multi-component anodes have been developed to improve on current ones. From research, tin silicon anodes have been developed which yield substantial improvements in battery performance. They have 3 times the capacity of graphite anodes and are much more stable than silicon alone, which increases the lifespan of the battery. Only small amounts of tin are needed to gain these benefits. The increase in capacity is the most significant to improving batteries for electric vehicles. Silicon-graphene anodes are another type being researched and developed for lithium-ion batteries, which yield similar benefits. By looking at properties, processing, and structure, the path to improvements in lithium-ion batteries can be clearly seen. Compared to gasoline, lithium-ion batteries have a few advantages. They enable vehicles to use electricity that may be generated by renewable or nuclear energy, thus reducing greenhouse gas emissions. Furthermore, they are more financially competitive because electricity costs are lower and fluctuate less than oil. Compared to other batteries, lithium-ion have the highest energy density by weight among all rechargeable batteries. They also contain a minimal amount of hazardous and toxic elements relative to other batteries. Lithium-ion batteries also have a better cycle durability than most batteries, and generally require little to no maintenance whatsoever during their entire lifetime. Thus, lithium-ion batteries are likely to continue being the most popular choice for electric vehicles. The future of electric vehicles is very promising, with plenty of opportunities and possibilities. With advancements in material science, battery energy density will likely continue to improve without significant increases in cost. In addition, the growth of infrastructure that supports electric cars, such as charging stations, will magnify the effects that technology improvements have on the market of electric vehicles. Thank you for watching our video.